In these videos, we'll talk about how to find the matrix for a linear transformation. We're going to begin with a review of what it means for a function to be a linear transformation. So there are two properties that have to be satisfied. The function, when applied to a sum, it has to be the same as the function applied to each of the parts of the sum, where we add after we apply our function. And our function must preserve scalar multiples. So if we take the function of a multiple of x, it's the same thing as applying our function to the vector x and then multiplying by our scalar. So an example of something that is a linear transformation is the function from r to r, t of x is equal to 3 times x. So for example, if we have x plus y, well, this is 3 times x plus y, which is 3x plus 3y. And that's the same thing as t of x plus t of y. Similarly, if we have t of k times x, this is 3kx. We can always pull out this k. We get k times 3x, which is k times t of x. Okay, so this is an example of a linear transformation. How about a non-example? So something that's not a linear transformation. Let's look at the squaring function. If I take the sum of two numbers, x and y, if I square them, if I square that sum, I get x squared plus 2xy plus y squared, which is not equal to x squared plus y squared. Okay, so this is not linear. Okay. Next, we're going to look at another way of showing that a function is a linear transformation. Another way of thinking of linear transformations are just as functions where we get our output by multiplying the input by some fixed matrix called the standard matrix. So given the input vector x, to find our output, we calculate a times x. Such functions are called linear transformations. So in the example, f of x equals 3x. Here we have just a little 1-by-1 matrix, which is equal to 3. Let's think about what kind of matrix this standard matrix A should be. First off, we're going to start by looking at the domain. So if we have a linear transformation that sends vectors in Rn to vectors in Rm, our domain is Rn, so that means that our vector x here must be in Rn. So it's going to be an n-by-1 vector. For this matrix multiplication to make sense, we need to have n columns in A. Next, we want that this linear transformation produces vectors that live in Rm. Remember that a matrix multiplication ends up just taking linear combinations of the columns of A. So AX is going to be a vector in Rm. So we need that we have m rows. So each column in the matrix A needs to be a vector in Rm, m rows. Therefore, this matrix A is going to be m by n. this sometimes feels a little bit backwards to folks. So we can see this map T goes from Rn to Rm. People naturally expect that A is going to be n by m, but it's not this way. It's always going to be, we're going to see the domain in the number of columns. We're going to see the target set in the number of rows. Then, to find this matrix A, all we're going to do is calculate the linear transformation of basis vector EI, the standard basis. So EI is equal to 1 in the ith row and 0 everywhere else. Okay, so we're going to calculate the image of EI under the transformation T, and that's going to make our ith column. Let's see this in some examples. Our transformation T is going to map vectors in R2 to vectors in R2. And it's given by sending xy to the vector 2 times y, 0. We'd like to find its standard matrix A. So A is going to be 2 by 2. And to find the first column of A, what we're going to do is we're going to calculate T of the vector E1, which is just 1, 0. Okay, so our x here is 1, our y is 0, so the result is 2 times 0, which is 2 times 0, 0. This gives us the vector 0, 0. Okay, so first column done. It's going to be 0, 0. To find the second column, we're going to calculate T of E2, which is T of 0, 1. Here, x is equal to 0, y equals 1. And our rule for our output is that we're going to take our y value and multiply it by 2. So we get 2, and then we have 0 as our second coordinate. So our matrix A is going to be 0, 0, 2, 0. Now, we can check this by calculating A times xy. What it should produce is the vector 2y, 0. Okay, so let's try this out. We've got 0, 2, 0, 0. We're going to multiply it by this generic input xy. We do the matrix multiplication, we get 2y, 0. This checks out. It's equal to our original, it's equal to our output for T of xy. All right, we have another example of a linear transformation. We want to find its standard matrix. This map is going to send vectors from R3 to R2. How can we tell? Well, we look at its input. These are vectors with 3 components, and its output is a vector with only 2 components. This tells us that the matrix A is going to be 2 by 3. Okay, to find A, what we're going to do is calculate T of the vector 1, 0, 0. That's going to be our first column. Then our second column is going to be T of 0, 1, 0. And our third column is going to be T of 0, 0, 1. So we're just going to find the image of each of our standard basis vectors. Okay, what does T do to the vector where x equals 1, y equals 0, and z equals 0? We get 1, 2. Okay, what if x is 0, y is 1, and z is 0? We get 1, 0. Okay, What if x is 0, y is 0, and z is 1? We get 1, negative 1. And so this is our standard matrix A. And we can check that we've done this calculation correctly by multiplying A by this vector x, y, z. So we take our matrix A, we multiply it by the vector x, y, z. And what do we get? For our first component, we have x plus y plus z. For our second, we have 2x minus z, which matches the output that our linear transformation produces. Now that we're more familiar with this tool of finding the standard matrix, we're going to use it to decide whether or not a function is a linear transformation. So our plan is we're going to build a standard matrix, then we're going to compare the output of multiplying the matrix A by x, and then calculating t of x. If they produce the same output, then it is a linear transformation. If they have different outputs, it's not linear. Okay, so let's get started with this example. This map sends vectors in R2 to vectors in R3. So that means that A is going to be 3 by 2. And if this map is linear, A is going to have columns that are t of 1, 0 and t of 0, 1. Okay, t of 1, 0 is going to be 2, negative 1, 1. Okay, t of 0, 1, we have x equals 0, y equals 1. So our output is going to be 0, 1, 1. All right, and now we can move on to part 2. We're going to compare A times a vector x with t of x. So A times xy is given by, it's going to be 2x negative x plus y, y. And you might have been wondering where that matrix was from. It was just a mistake. So our result is 2x negative x plus y, and our final coordinate is x plus y, which we can see is not the same result as t of xy. So that means that our function is not linear. Okay. Where did we see that? Again, we look at this final coordinate, which is x plus y, and that differs from this final coordinate of 1. If all that we know about our linear transformation is what it geometrically does, this might seem like hard to write down a formula. Luckily for us, if we set out to find the standard matrix for our transformation, all we need to know is what happens to our standard basis. So for example, here, if we're looking at a linear transformation from R2 to R2, we only need to worry about what happens to just 2 vectors. Okay, so let's try this out. We want to find the standard matrix for this linear transformation. Because it's mapping from R2 to R2, A is going to be 2 by 2. And A is going to have, the first column is going to be what happens to the vector 1, 0 under this transformation. And our second column is going to record what happens to the vector 0, 1 under our transformation. Okay, so let's start by finding t of 1, 0. We start with the vector 1, 0. And then what do? We're going to reflect it across the line y equals x. And this is going to produce the vector 0, 1. And then what are we going to do? We want to then rotate it by 45 degrees. And since a direction isn't specified, we're going to just do the normal one of going counterclockwise. So this vector 1, 0 is going to rotate over to here. Okay. All right, so its coordinates are going to be negative square root of 2 over 2 and square root of 2 over 2. Right. We can see our x coordinate is negative, our y coordinate is positive. Okay, and I should really be writing this as a column vector. All right, next up, let's find what happens to t of 0, 1. So we start out with the vector 0, 1. We're going to reflect it across the line y equals x. So it's going to reflect over to 1, 0. And then we're going to rotate it 45 degrees. So it's going to rotate up to actually lie on this line y equals x. Okay, so t of 0, 1 is going to be square root of 2 over 2, square root of 2 over 2. And so we have found our standard matrix A. And in order to find our formula for this map, all we need to do is take A and multiply it by the generic vector xy. So t of xy is A times xy and so we get the formula. Our first coordinate will be negative square root of 2 over 2x plus square root of 2 over 2y. Second coordinate is square root of 2 over 2x plus square root of 2 over 2y. Okay, so just by finding the images of these two vectors, we can write down a formula to find the images of all vectors.